Welcome to topology class. Last class we have discussed about subspaces and we have seen the topology in the subspace is going to be the topology from the parent set that is restricted to this subset. Today we will discuss about hereditary properties. Today our topic is hereditary property. Hereditary properties. You might have heard about Gregor-Mendel's experiment and all. Okay, what was that? It is something related to hereditary property only. So what was that? Gregor-Mendel experiment and all you studied in your biology, right? Uh, TR, something like this, then TR, be like this. That means Gregor-Mendel experimented the plants having height, tallest one and shortest one, then take its cross, and he developed some more terms, that is TT, uh, small tt, like that. So many varieties, and he was studying about these hereditary properties. Now, what is hereditary property? Hereditary property means a property. In general speaking, I am saying hereditary property means as a property that is transferred from generation to generations. That is, if a father is having certain quality, then the son is also having same quality, same character, and his son is also having same character. We will say that such properties are hereditary one. Okay. So in topology, let us see what's the definition of hereditary property. 4.2 definition. A property of a topological space, a property of a topological space is said to be hereditary, is said to be hereditary if whenever a space has that property, a space has that property, then every subspace of it has that property. That means a property of a topological space is said to be hereditary if whenever a space has that property, then every subspace has a property, not that, has a property, then every subspace of it has that property. That means if you are having X2, okay, suppose this is your topological space X2. Now you can have subspace here, lots of subspaces. These are going to be subspaces. And if I am naming this one as X1, this is X2, X3, X4, and XY. Okay. Now, suppose X2 is having a property P. Then, when I am considering my X1, X2, X3, X4, and XY, all the subspaces. These all should have the same property P. Then we will say that this property P is a hereditary property. Can you follow me? If a space has got a property, then every subspace of it should have the same property. Such a property, we will say that it's a hereditary property. We can have certain examples. Example, being an indiscrete space. Being an indiscrete space. Being an indiscrete space means our XO is indiscrete. Indiscrete means so should contain only two sets. One is what is empty set and the entire set. Now we take any subspace of this. The topology, this D is respect to that set should be same as this, right? So being an indiscrete space is an hereditary property. Second one, being a discrete space. Being a discrete space. Being a discrete space. And next one, metrizability. Metrizability. We will see this all in detail in further classes. So just I am naming the properties. And fourth one, second countability. What was second countable? We say that S base is second countable. It should have a countable base. So these are some examples of hereditary properties. Now, non-hereditary property, examples of non-hereditary property. First one is compactness. Compactness. Are you saying that compactness is not a hereditary property? You consider real line with usual topology. With usual topology. Okay. Then we will have open interval 0, 1. This subset of R, right? Now we can have the usual topology restrict to closed interval 0, 1 also. So it will form a topological space. Now, can you say that 0, 1 is compact? Okay, I will make it somewhat clear. So I have taken this. Then let me take closed interval. Some 0, 1 is also will work. 0, 1. Oh, rest is the reverse order, right? See, like this you take. Now you know that this set is compact, right? But this one is not compact, right? We have studied one theorem that a closed and bounded set in real number is compact. But this is not closed even though it is bounded and it is not compact. So compactness is not at all a hereditary property. Second one, connectedness. Connectedness. What was connectedness? It is not possible to write a space as a union of two separating sets, right? Definition you have come across in your real analysis classes. Now, connectedness is not a hereditary property. Since we can list out so many examples, I'm listing out in R. Since R is connected, But you can take 0, 1 union 2, 3. Will it be connected? Is not connected. So we have said that hereditary means it should be transmitted to every generation, or if we are taking in terms of topological spaces, every subspace of it has got the same property. Here R is connected, but this space is not at all connected. So connectedness and compactness are not going to be hereditary properties. Now 4.3 proposition. Let script B be a base for a topology T on a set X X and and let Y subset of X. Now we should have a topology there. So let B restrict to Y. So that should be of the form some B intersection Y for some B belongs to script B. Okay. Then this B restrict to Y is a base for the topology, is a base for the topology T restrict to Y on Y. So what does this proposition says? Proposition says that once you know the base of a topological space, you can easily find what is the base of a subspace. So if B is a base for a topology tau on a set X and Y is a subset of X, then we can have the script B restrict to Y, script B restrict to Y, that's equal to set of all B intersection Y, where B belongs to script B. Then this B restrict to Y is a base for the topology T restrict to Y on Y. So let us prove it. Proof. Let Y belongs to Y. Small y belongs to capital Y. And G be an open set in Y containing small y. Then this G equal to some H intersection Y for some open set H in X. Now what we will check is the characterization of a base. If a point is given and an open set containing that point is given, then if we can find a base element B such that Y belongs to B and this B is contained in G, then we will say that the collection B is a basis. So we will check here like that. So here you are having this is your X. In this X you have got a topology tau, right? Now you are having a subset So this is going to be your subset. This is your y, and this here we have got a topology T restricted to y. Okay, that is in this topology. Now what you're going to do is you will take a point over here. Okay, this point is your y. Now you will take an open set which containing this y. So I'm going to take an open set which containing this y. So this is going to be my open set containing y. So this is G. So I have got y belongs to G, comma G is open where in T restricted to y. See, in this space only, this y is, G is open. Now, in this topology, we know the open sets will be of the form, some open set in X intersection with Y. So, I can have some H intersection Y where H is open. Instead of saying open, we should say that H belongs to the topology. So H belongs to top. So this was we have mentioned here. So let Y belongs to Y and G be an open set in Y containing small y. Then G is equal to H intersection Y for some open set H in X. Since Y belongs to G, Y belongs to G and G equal to H intersection Y, which implies Y belongs to H, right? So by characterization of base, we get there exists a B belongs to script B such that this Y belongs to B and B is contained in H. Therefore, Y also belongs to G, right? So this Y belongs to, since Y belongs to G, we get Y belongs to B intersection Y, right? B intersection Y, and B intersection Y is contained in G, and B intersection Y is definitely contained in T restricted to Y, right? Which is open. This proves that this proves that this script B restricted to Y is a base for this T restricted to Y on Y. On Y. So we have proved if a base of a topology is given, the subspace we can easily find it out as that base restricted to Y. Now 4.4 corollary. Second countability is a hereditary property. Second countability is a hereditary property. Hereditary property. So we want to find that a space X is going to be second countable. That means it should have a countable base. Then every subspace of it should have a countable base. That's the thing we want to go. So it can be easily reduced from the previous result. Proof. Let X2 be a topological space with a countable base some B, and this Y subset of X, then this B restrictive Y as defined above is second countable and is a base for T restrictive Y, hence the corollary. See, from previous theorem, we have seen that whenever B is a base for the topology T, then B restrictive Y will be a base for the topology T restrictive Y, right? Then suppose your B script B is countable. Suppose this B is countable, then definitely this set should be countable. So that will be the base for Y. So every subspace of a second countable space is second countable. So we can easily find that result second countability is a hereditary property. Now 4.5 theorem. Metrizability is a hereditary property. Metrizability is a hereditary property. Metrizability is a hereditary property. Proof. Suppose X2 is metrizable. Let D be a metric. Metrizable means its corresponding topology can be obtained from a suitable metric. So let D be a metric on X, which induces the topology top. Let Y subset of X and E be the restriction of D, the metric D, to Y cross 1. Now E is a metric on Y. This you have studied in your real analysis class. Whenever you got a metric, its restriction to a subset is going to be another metric. So here we have got X2, the topological space, and that is metrizable. So there should exist a metric on that. Let that metric be small d. Now you restrict your small d to the set Y cross Y. And that restriction we are saying that it is E. We claim that E induces the topology T restricted to Y on Y. T restricted to Y on Y. So this was our claim. We want to prove this one. Let BD XR, nothing but the open set with respect to the metric D. BD XR and BE YR are the open balls are the open balls with respect to D and E respectively. D and E respectively. Note that if Y belongs to Y and R greater than 0, then BEYR is equal to BDYR intersection with Y. Thus, BEYR belongs to T restricted to Y. So first we are proving that BEYR that can be written as BDYR intersection with Y. Then this is nothing but a member in the topology. Now let script U be the metric topology. That means metric induced topology. Metric topology on Y induced by the metric E. Now what we want to show is U is nothing but this T restricted to 1. Thus we have to show that thus we have to show that this U is nothing but T restricted to 1. U is equal to T restricted to 1. Let script B be the family of open balls with respect to E in Y. B be the family of open balls with respect to E in Y. Then this B is a base for U. Because you are taken like that. U be the metric topology. So family of open set means we are using the metric to define it. So definitely this B collection B will form a base for U. And thus your B is contained in T restricted to Y, right? If you are taken like that, so what you're having, B is a base of U. That means U is contained in this T restricted to Y. So we have got one part, right? So if you're having one part, called as 1. Conversely, let G belongs to T restricted to Y. See, we want to show that two family of subsets are equal. That means one is contained in the other we want to prove. So one part we have already proved. Now the converse part, let G belongs to T restricted to Y. Then G is of the form G is of the form G equal to H intersection Y, where H is open in X, where H is open in X. Let G belongs to T restricted to Y, then G is of the form G equal to H intersection Y, where H is open in X. Now for each Y belongs to G, now for each Y belongs to G, G is of the form H intersection Y, right? So that's equal to H intersection Y, right? H intersection Y implies Y belongs to H and Y belongs to Y, right? Therefore, there exists some Ry greater than 0 such that BD YRY is contained in H, right? Because H is open. So H is open means every point is going to be an integer point. We have studied that. That means in particular for this Y also, the H, okay. Now this is where Y means there should have some open set which come or the which completely contain inside H. So this is Y with radius Ry. So BD YRY is contained in H. Then BD Y comma RY intersection with Y is contained in H intersection Y. That is BE YRY, right? BD, this intersection Y means we have already seen that it's nothing but BE YRY, which is contained in H intersection Y means G, which implies, what does this implies? From this we can easily imply that this is contained in G. So you take each Y belongs to G, then G can be written as G is equal to union Y belongs to G of this open set B E Y R Y, right? Thus, what you proved, thus G is union of open sets with respect to E on Y. Hence, hence, what are you having? Hence, G belongs to U, G belongs to U. We have started with G be an open set in T restricted to Y. Now we've got G belongs to the topology U. Thus, T restricted to Y is contained in U. Equation 2. So we have already seen that the reverse one. So now you got this is contained in. So this together implies that your U is nothing but T restricted to Y. Or you can say that Y, then T restricted to Y is metrizable. Thus we have proved that Y is metrizable. You have taken a topology X and Y, a subset of X, and you have proved that this Y is metrizable. So today's class we have discussed about the metrizable property. Okay, so go through this notes. If you find any doubt, uh, let's free to ask me the doubts. Then I am winding up today's session here. Thank you for your patient listening. Thank you.